so I can't even believe that I have to do this again because of the volume. This is taking 8 years. Alright, so I'm going to pick up where we left off and just kind of explain to you because I already wrote the notes out in the first video that didn't pick up the sound. Alright, so you graph the original, f of x equals x. It's called the parent function, and then we transform and or do things to it. Okay, but the original is called the parent function. So there's the original parent function. This told me, according to my transformations, to go up 2. So I took the intercept, moved it up 2, kept the slope the same, regraphed. Okay, so now the slope is the same, 1. The y-intercept's now 2. So I wrote it out, g of x equals x plus 2. Alright, if I go too fast, pause it, rewind it, whatever you gotta do. Over here, I know this transformation from the list means I should go right 6. So I graphed the original parent function, took the intercept, moved it right 6, kept the slope the same because there was no stretch, and then labeled it. So this now has an intercept of -6, slope of 1. So this is the function. Same thing over here, according to the list and memorization. This is a reflection. Then this is down 3. So I take the parent function, which is here, move it down 3, and now I'm going to have a negative slope, but it's going to still be 1. Regraph it. Y-intercept is now -3, slope is now -1. Rewrite it. Same thing over here, but now it's a stretch. So because the intercept is 0, the 0 doesn't move, but if our intercept is not the origin, then the stretch will change the intercept as well. So I change my slope to 4, so I start at 0, up 4 over 1, regraph, label. Over here, left 4, up 2, so take the original, go left 4, and up 2, okay, left 4, up 2. New y-intercept is at 6, slope is still 1, so that's your equation. Okay. Now, going the reverse. I give you the parent function, give you the shifts, you write them down. So this is straight memorization off of the list. So take a second to write those down or pause it. Okay, now here we're going the opposite way. Give you the line. You write what happens. The original is f of x, so that's the line through the origin. So this went up 3, but it's impossible to tell whether it went up 3 or left 3. I know the line's a tiny bit off, but it should be the dot should be here. So it's either going up 3 or left 3. Since we can't tell, I would have to accept both of these answers. Okay, here I count my slope as 1/3. So from the slope moved from 1 to 1/3, the y-intercept stayed the same. So that was a compression. Here I have a reflection. So it's now negative, so that goes up front. And then it's +1. So those are the transformations that happen to that parent function. Okay, so now getting a more complex parent function, instead of just f of x, we actually have a more complex line. We have 2x plus 3. But the transformation is still to go down 3. So I graph the original, I move it down 3, I look at my new y-intercept, and my slope actually stayed the same. So, because there's no number out here. So I write the new function in terms of x. This is what I was talking about with the stretch, if the intercept's not the origin. So here my intercept is actually, my y-intercept is actually 5. So if you imagine yourself standing, here you are, and I took my hands on your head and your feet, and I pulled you, I stretched you. If this is your belly button, well, when I stretch you, your belly button's also going to move. Your head's going to go up here, your belly button's going to be there, here will be the rest of you. Okay, so your belly button's going to move. So it makes sense that the intercept would also get stretched by a factor of 2. So, or you can think about distributing it in. So the intercept actually becomes 10, the slope becomes 2, and then you graph it. Okay, and that was it. So that's the end of part 2. The volume, I hope, really worked this time.